Gels contain microscopic particles known as colloids that are suspended in a liquid. They form when condensing colloids try to phase separate, but instead get trapped into a network of particle strands and liquid-filled pores. In our previous video, we showed that phase separation slowly continues as a gel ages, but this only deepens the gel's arrest. In this video, we explore how to break that arrest and let the gel flow. Gels do cool things when they flow, but they can also be annoying. For example, consider pouring ketchup. The ketchup barely moves under gravity, but give the bottle a whack and it starts to flow. Sometimes a little too well. Let's model it. We place the gel on a surface and lift one end. This incline creates a constant shear stress on the gel with a magnitude that depends on the angle. A small incline angle creates a weak shear stress. Increasing the angle increases the shear stress, eventually causing the gel to flow. Even though we think of ketchup as a liquid, it behaves like a solid under weak shear stress, becoming a liquid only under stronger stress. Using our simulations, we can zoom in and see what's happening inside. We impose a constant shear stress on the gel and measure how far it deforms in terms of bulk strain and how fast it deforms in terms of the strain rate. Our first case is a gel with weak shear stress. Like our ketchup, this gel deforms, but it never flows. Under strong shear stress, the gel deforms like a solid, then yields and begins to flow. If the stress is strong enough, it just keeps flowing. But in the intermediate case, we discover something different. Here, the gel initially creeps, then it yields and flows, but this time it resolidifies, despite no change in the applied stress. Our simulations were the first to show this unexpected behavior. With more cases, a clear trend emerges. Under weak shear stress, gels maintain solid-like behavior. They creep, but they never yield. Under strong stress, gels creep, but after a delay, they'll yield and flow like a fluid. And between these extremes, we see gels with initially solid-like behavior that then flow and later resolidify, even though the applied stress has not changed. Interestingly, every gel that yields does so at the same critical strain. This suggests there's a specific microscopic mechanism at work here. The colloids inside a gel form physical bonds when close to one another due to attractive forces 5 to 10 times stronger than Brownian forces. When a gel yields, we might expect it's due to many of these bonds breaking. But in our simulations, the particle network stays largely intact, even when the gel flows. To track these changes, we divide the total number of bonds at any time by how many bonds there were when the stress was first applied. This gives the net gain or loss of bonds, including effects of both aging and applied stress. Let's look at this for our 3 cases. For gels that never yield, the number of bonds increases over time. In contrast, a gel that fluidizes under strong stress loses bonds. Finally, in our intermediate case, we see both behaviors, a loss of bonds as the gel fluidizes, followed by a net gain in bonds as it resolidifies. This technique demonstrates for the first time a one-to-one correspondence between microscopic bond dynamics and the macroscopic behaviors of creep, yield, and resolidification. Quantitatively, though, there is a big surprise. At the critical strain where gels yield, fewer than 0.1% of the gel's bonds have broken. So what's happening on the microscopic level that allows this bulk yield? Individual colloids in a gel experience Brownian motion, a random walk caused by molecules from the surrounding liquid bombarding the particle. Since Brownian motion heals disturbances by distributing colloids uniformly, we might expect Brownian motion to heal broken bonds and delay yield. To test this idea, we simulated gels under the same stresses, but with Brownian motion shut off. We found that Brownian motion decreases the delay time and lowers the yield stress. That is, instead of healing the gel, Brownian motion actually facilitates yield. This makes sense if we examine bond dynamics. Under shear stress, the bond between colloids is stretched to its weakest attachment point, and a Brownian kick can then break it. So Brownian motion gives the applied stress the extra push it needs to release the gel from arrest. When sheared, gels show complicated flow behaviors. They can creep like a solid, flow like a liquid, and even resolidify. Our work shows that these states correspond directly to small changes in the number of bonds between colloids. This implies the mechanical yield of these weakly sheared, reversible gels is a release from kinetic arrest and may be a step forward in phase separation. We'll continue exploring these ideas in our next video, which looks at how gels collapse under gravity.